Hey everybody, today I'm going to be talking to you about the periodic table, how it was developed, and how to use it. Now, the periodic table was developed because it used to just be that chemists had a list of elements, and at first maybe just in alphabetic order. Then they decided, once they started figuring out the atomic masses of the elements, they could arrange them by atomic mass. Then other people decided that, there are repeating patterns of every certain elements, their chemical properties are similar, and so they started to arrange them by their chemical properties. Finally, someone named Dmitri Mendeleev came along. He had a dream that inspired his version of the periodic table, and what he did is he arranged them by mass, grouped them by their chemical properties, but his real baller move for his periodic table is that he left gaps where he thought that there should be elements. And other people had done that too, but he used his periodic table to not just say there should be elements that are not discovered yet. He used his periodic table to predict what their properties would be. What are their chemical properties? What's their atomic mass going to be? And then later people would discover elements like gallium and germanium, and they would fit in his boxes that he left open in his table. Now this is really impressive because people didn't even know what protons were or that an atom even had a nucleus. It wasn't until 40 years later that experiments discovered that there was a nucleus and the nucleus had a charge. Mendeleev also decided to switch two elements, iodine and tellurium. Even though it didn't match their masses of increasing masses, he thought that because things should be arranged by their chemical properties, that those two fit better. And then once experiments happened 40 years later to realize that it should be the number of protons or the charge in the nucleus that better predicts where they should go on the periodic table, they realized that Mendeleev made the right move. So now I'm going to talk to you just about the groups of the periodic table and how to use it. So we've got a periodic table right here, an example of one, and it's an arrangement of all of the chemical elements that are grouped into columns called families and groups, and rows called periods, where the elements that are in a column or in the same group have similar chemical properties. Now, because they have similar chemical properties, whether things are something like a metal or a non-metal, those are all located in similar places on the periodic table. Metals are all of the elements starting here with lithium and going down. They're all of these in the middle. And they're all of these up to this point, so aluminum, gallium, tin, bismuth. These are uncategorized. They haven't had enough atoms of them to properly classify them in terms of their character. These also, however, are metals. So most of the elements on the periodic table are metals. The properties of metals are that they are shiny, they are ductile, meaning that you can move them, they can bend, they can be stretched into wires, they conduct heat and electricity well, and that they give up electrons in reactions with nonmetals. Now, within the general category of metals, there are some specific areas and groups that we want to talk about, from lithium down to francium. These are called group 1 metals or alkali metals. Group 2 metals or alkaline earth metals are from beryllium to radium. All of these in the middle are called transition metals. These, gallium, tin, bismuth, and this area are called post-transition metals. And here, these sections at the bottom are called lanthanides and actinides, and they are called post-transition metals. They're incredibly reactive with other things aside from water, and they react by losing one electron. They have one outer or valence electron. Group 2 metals are similar to the alkali metals. Those would be the ones like beryllium, magnesium, calcium, strontium, barium, and radium. They're called alkaline earth metals. They're reactive more than most other metals, but not as reactive as the alkali metals. They also react with water, producing a type of hydroxide, which would turn the water basic or alkaline. They also produce hydrogen gas. They just are not as reactive. They react by losing 2 electrons per atom of that element, and it's because they have 2 outer or 2 valence electrons. The transition and post-transition metals are what most of the metals are, and they are not terribly reactive compared to group 1 and group 2, and they're, because of that, useful in industry, in creating things. The last type of metal that I'm going to cover would be the lanthanides and actinides, called the inner transition metals. The reason that they're called inner transition metals, notice the numbering, that we go here from 56 down here to 57, and then 58 through 71, and then we move back here to 72, 73, 74. So the reason that these are on the bottom is really just because they should be here and the entire periodic table should be wider. It just wouldn't fit as nicely on a sheet of paper. You can see based on the color coding, the red elements are ones that do not occur in nature. Anything past uranium does not occur in nature on Earth, and they have been created in labs or in particle accelerators. You can see some others that are color coded that way. That's what the red color coding means here. Nonmetals, to compare them to metals, the nonmetals are here, starting with carbon, phosphorus, selenium, iodine, and radon, and going up this way, as well as hydrogen. Those are the nonmetals. There are much fewer of them compared to metals. They do not conduct heat and electricity well. They insulate better. They're generally not shiny, but dull in appearance. They're not generally malleable or ductile. They are more brittle. And they tend to gain electrons in reactions. There's some key parts for the nonmetals as well. This last column on the periodic table, helium down to radon, those are called the noble gases. And these elements, fluorine down to astatine, those are called halogens. The noble gases, the group 18 on the periodic table, they are gases at room temperature. They're almost completely unreactive in terms of their chemical reactions. Radon is here at the bottom, and the reason that people still need to be aware of radon, even though it's chemically unreactive, it is nuclear reactive, that it gives off radiation and eventually will turn into lead. If you breathe in radon gas into your lungs, it will emit radiation that can damage your lungs and then also turn into lead atoms through a nuclear reaction. Group 17, the halogens, things like fluorine, chlorine, bromine, iodine, they're the most reactive nonmetals, and the reason that they are the most reactive is that their outer shell, their valence shell, is almost full of electrons. They're only short by one, and so they react by gaining one electron per atom. The last category we're going to talk about would be the metalloids. Those would be boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. And those really just have a combination of metallic and non-metallic characteristics. So a classic example that it has a combination of metallic and non-metallic characteristics would be silicon. It is known as a semiconductor, and so it doesn't conduct electricity, it doesn't insulate against electricity. It's called a semiconductor and is therefore very valuable in electronics. So the goal with this video was to give you the information that you would need to know so that you can take a periodic table, you can find an element on it, and you can use its location on the periodic table to predict some properties of it. And that's really how we say that the periodic table is used as a tool. It's a tool to predict properties of the elements based on their location, that they're not randomly placed on there.